Hello. Hello, good morning. ¿Se oye? Good morning. Good morning, everyone. Shall we start? It is a great honor and real pleasure to host Alex Babanin and introduce him to yourself. Alex Babanin will be here with us for today and tomorrow, delivering this seminar and two other parts of continuous lectures on the same topic. And also will be assisting us and listening and discussing with the students of our group several presentations during today and tomorrow. The agenda for today is this one, and for tomorrow we will have another lecture, the third part, and several students talking among us in the meeting room at the fourth floor. So as I said, it's a great honor to have Alex Babanin here. Alex Babanin is professor in ocean engineering and director of the Center for Disaster Management and Public Safety at the University of Melbourne, Australia. He got BSc in physics and Masters in Science in Physical Oceanography from the Lomonosov Moscow State University in Russia. He got the PhD in Physical Oceanography, again, from the Marine Institute in Sevastopol, Russia. He has worked as a research scientist in the Marine Hydrophysical Institute, as an academic in the University of New South Wales in Canberra, Australia. He has also been in the University of Adelaide in South Australia and Swinburne University of Technology in Melbourne. Areas of expertise, research, and teaching are wind-generated waves, maritime, coastal, and Arctic engineering, air-sea interactions, ocean turbulence and ocean dynamics, climate, environmental instrumentation, and remote sensing of the oceans. These include extreme meta-ocean conditions from tropical cyclones to Arctic and Antarctic environments. He has lots of papers, more than 400 publications in peer review. And as I said, it is a great pleasure to have him here. And We will start with this first part of his talk on wave couple impacts in the lower atmosphere, including sea drag, wave boundary layer, CO2 transfer, and extreme metocean conditions. Then, Alex, is yours, the floor, and switch computers. For those interested in the agenda, there is some printed versions.
Very nice. It's always surprising when the modern technology actually works. Thank you, Paco. Thank you, Pedro, for organizing this seminar. I know it's Christmas time. Merry Christmas. And it's a great pleasure to be here. I spent hours and hours, days and days at this very podium, right? Was it a WISE meeting? It was an International Waves meeting here, and then there was the lecture course, which Paco mentioned, 2018, something like that, right? So it's a very familiar environment, and some faces are familiar, so it's so nice to be back. The topic of wave-coupled impacts is actually very big. It's different to what I see. So, okay, how do we do that? Yep. You know, like I mentioned, the WISE meeting, which was here in this auditorium, that's the meeting about waves, right? So people who study waves, that's a big topic in its own right, fluid mechanics and wave forecast models and everything, they come to these meetings, right? Now wave-coupled impacts, right? It's related to the waves, but as a science, it's much broader. And it requires all sorts of different expertises, right? The waves interact with obviously they're generated by the wind, right? But then they change the very winds which generate them, right? So they interact with the lower atmosphere. And this is what we were going to be talking about today. Paco asked me to talk on the topics of the wave atmospheric boundary layer interactions. And I prepared first abstract, and then I prepared the lecture slides, and I realized that it's too big. I promised so much in my abstract that I can't deliver that in 1 hour, right? So we split it into 3 seminars, right? The first seminar is now. I'll do main introductions to that, to the sea drag, which is due to the momentum flux from the wind to the waves, right? And we'll discuss in details the parameterizations of the sea drag. And then the actual way the waves work with the wind, the topic of the wave boundary layer. And what else you see in the abstract, the extreme conditions for wave wind interactions, that's the second hour today, right? And the actual modeling of the Earth's interactions with participation of the waves, which is the CO2 transfer and spray production and modeling of hurricanes, that will be tomorrow, right? But before we get into wave-coupled effects in the low atmosphere, just a couple of minutes on other wave-coupled effects, right? This is a conference which we're holding in Melbourne in just about a month, right? So if you haven't submitted our abstracts yet, and I know you haven't because I prepared the program just a couple of days ago, there's nobody from Mexico, right? There is still time, right? So this conference, and it's the 6th on wave-coupled effects. Apart from ERC fluxes in the atmospheric boundary layer, which is our today's topic. They include the interaction of the waves with the upper ocean, right? And the words are nearly the same: interaction of the waves with the wind, or interaction of the waves with the ocean circulations. But the science is completely different, right? That's how the waves affect the upper ocean. It's a different discipline to how the waves interact with the wind. All right, and then there are a couple effects in this conference, right? In this discipline of wave large scale interactions, is the waves in the large scale systems, including climate, right? Just very briefly what it is, right? Let's say in the changing climate, the winds are increasing and the waves are increasing, which we know they are, right? Then the waves, for example, they produce extra turbulence, right? The waves, they produce turbulence in the air, and that can mix through the thermocline, right? And below thermocline, the water is cold. So if you mix through the thermocline, you involve colder waters and you cool the ocean surface. And if the ocean surface gets colder, it interacts with the atmosphere. It cools the atmosphere. And it's not a small effect, because the heat capacity of the entire dry atmosphere is the same as heat capacity of 2 meters of the ocean water. And the ocean is 4 kilometers deep, right? So if you change the mixing of the ocean a little bit, right, that can have a big effect at a very large scales, at the atmospheric scales, right? And until recently, we didn't pay attention. We don't still, in many models, don't pay attention to that. But that's a part of this wave coupled topics. And of course, there's section 6, which you see very broad, where everything else is included. The waves produce turbulence, the waves produce bubbles and facilitate the gas exchange, the waves produce acoustic noise in the ocean, right? The wave breaking and whatever the acoustic applications are, right? You have to couple the acoustic models of the ocean with the wave models. And the waves big part in the sea surface remote sensing. Remote sensing, satellites have been flying for more than 40 years now. So they have provided global coverage of measuring of the ocean surface. They do that usually by interpreting some properties of the waves. For example, they measure the wind, but the satellites don't measure the airflow as such, right? They interpret properties of the waves on the surface to measure the wind. All right, so sometimes waves are a necessary signal. Sometimes you don't want them. For example, if you measure the ocean color and the waves breaking is very bright, it masks the ocean color, so you want to filter this out. So this wave coupled effects, both in physics and technology, are everywhere these days, because of course, when you deal with the ocean, you usually deal with the surface, and that's where the waves are, and they either facilitate all the fluxes or affect all your measurements there. But today we will be talking about the wave coupled effects in the low atmosphere, and in a couple of slides, I will explain why it's a low atmosphere, but it's not that low actually, right? And to introduce this topic, let me show a few figures here, which I borrowed from internet. Is that pointer?
This one?
Use.
No,
Yeah.
it's
Yep.
over there.
Yep.
For the people connected.
Yep. Okay, so there are people on online, then of course cursor is better, right? So we are talking about the waves in the atmospheric boundary layer, where of course there is wind which generates the waves. These are wind generated waves, right? Now the wind produces the waves, but the waves then provide the feedback and they change the very wind which generated them, right? Because waves are effectively and not effectively directly the roughness of the surface. Now, if we run meteorological models over a land, then the roughness of the land defines the friction at the surface, right? That can be crops, that can be rocks, that can be suburban environment, that can be ice if you are in the Arctic seas, right? But if you are over the ocean, all right, this is a water surface, what is your roughness? It comes from the waves, one way or another. But then this is not a constant roughness, right? Because once the wind produces the waves grow, the roughness changes, right? The waves have directional spectrum, right? And the wind is unidirectional, so they interact differently with the wind. The waves propagate. Is not the permanent roughness, unmobile. And the waves break. The breaking has a very big dynamic, as we will see in the second part of the lecture this afternoon, and so on. So wind produces waves, waves change the wind, and the waves involve these all fluxes. For the Earth's interactions change because of that. At some point, if the wind is very strong, it produces spray. Right, we're talking about winds greater than 20 meters per second. The spray starts to be produced actively by the wind, and that changes completely the dynamics of the boundary layer, right? Because when you have a lot of spray is the droplets of the water. Water is very heavy, 1,000 times heavier than the wind, right? So the dynamics of the boundary layer changes, but also heat fluxes change because spray evaporates, right? So there's a change to latent flux, but also the suspended droplets of spray, they increase the surface for the Earth's interactions, right? And the sensible heat flux also changes. So there's dramatic changes to the Earth's interactions if you start thinking about the processes connected to the waves. And usually we just parameterize it in terms of the wind speed, but the wind speed cannot describe for example, the spray production by the waves, right? So the spray is not produced by the wind. It's water. It's produced by the waves. So the few pictures here on the left, they illustrate these interactions. On the right, you see this exchange of energy, which comes from the sun, goes through the atmosphere, which is near transparent for the sunshine energy, goes through the surface, warms the ocean. It warms the ocean not uniformly because of latitudes, because of continents, currents, islands, and so on. And then the energy which came from the sun to the ocean is passed through the surface again, back to the atmosphere, because it creates pressure differences in the atmosphere, right? If there are pressure differences, the winds will be created, right? If there is big pressure, large pressure here, small pressure over there, there will be wind. And because of the Coriolis force, it will be spinning. The cyclones and the anticyclones are produced in the wind because of friction or work of the pressure forces on the surface. They create waves, and the energy goes back to the ocean, right? So the energy comes from the sun through the water surface, goes back from the ocean into the atmosphere, creating large-scale patterns. And then the winds, create the waves and pass energy and momentum back to the upper ocean, right? And that's the Earth's interactions. That's what drives weather and climate and ocean circulation. And we need to account for the waves if we want to produce those fluxes correctly. And that's the role of the waves. And some phenomena I mentioned here. You can see the bubbles, right, which are obviously produced by the wave breaking, and they facilitate the gas exchange between the atmosphere and the ocean, including CO2, which everybody cares very much these days. They produce spray, right, and they produce Ekman circulation and turbulence in the upper ocean, and so on. The second picture shows the Earth's interactions in the marginal ice zone. Right, it may not be so relevant for Mexico. I don't think there is a lot of ice here, but just in the general context of the climate, you can imagine these are big areas on both poles, around both poles. Waves can play significant role there, right? Because if the waves are big, they can break the ice. If the ice is broken, albedo changes, right? If albedo changes, the dark water absorbs heat, it can melt the ice. Unless the atmosphere is very cold, then the ice will refreeze, right? So the ice flows will spread over larger areas and the ice will refreeze. So that's truly coupled environment, right, which has a place for the waves, of course, and has a big place in the climate modeling in air-sea interactions at very large scales. At the very bottom, there is a tropical cyclone, right? That's it's a general name used in Australia, in America, North America, South America, they call them hurricanes, right? And the cyclones, they happen in the air, but that is a truly air-sea interaction phenomena, right? They call tropical cyclone for a reason, because they get energy from the warm ocean. Ocean must be warm, but that's not enough, right? There are other conditions for the air-sea interactions to be met for tropical cyclones, right? And then this heat flux from the ocean goes to the atmosphere, back to the atmosphere to increase the intensity of the cyclones. Obviously, that it goes through the surface covered by the waves, and the waves play very big role there. I will be talking about tomorrow about this tomorrow. So in the atmosphere, they produce spray, a lot of spray in the winds in excess of 30 meters per second, and that changes dynamics and changes the heat fluxes. On the ocean side, they mix the ocean, and if thermocline is not very deep, they cool the surface. And again, the sea surface temperature, the heat content of the upper ocean is a key property to impact on the intensity of the tropical cyclones, right? So wherever we look, it's the place for the wave-coupled interactions. And in the past, they were not ignored, but not even neglected, right? But they just belonged to different phenomena, right? So people who study turbulence in the ocean, very small process, that's one group of people. People who study waves, a little bit bigger than turbulence scales, is a different group of people, right? Like a WISE meeting, which happened here in this auditorium a couple of times, right? And that's a big group for a good reason, because there is plenty of applications for the waves. There is wave forecast, there is ocean engineering where the waves are important. So there are people who need, there is a need for experts with this expertise, right? And then there are weather modelers, and it's bigger scales, and there are climate models, even bigger scales, right? And those were different groups of people. Now, separated by scales of the oceanic phenomena, now the nature doesn't know that there are different scales, all of them connected to each other, right? And as we understand that better, of course, we can bring them together, but most important thing which allows us to do that these days, let's say last 10, 20 years, is the computer capabilities, right? Because in the past, you could speak as much as you want about coupling waves with the climate models, but you were not able to do that in practical sense, right? Because computers were not allowing you to do that, right? But now computer capabilities are so big that you can actually couple small-scale models like waves with the large-scale models, weather, tropical cyclones, ocean circulation, and even climate, right? So it's a nice place. It's a nice time to be in this place. And the sketch on the right is taken from an old paper of Professor Chalikov in our group. It shows how the waves, which the surface is over here, interact with the ocean below in schematic sense, and the atmosphere above. So we're talking about atmosphere. Now there is wave boundary layer, somewhere very close to the surface. We're talking about the scales of the wave height, where the direct influence of the wave orbital motion is sensed by the atmosphere. Then there is Monin-Obukhov layer. That's the regular semi-logarithmic profile, the constant flux layer in the atmosphere, like in any fluid mechanics surface. And then there is outer layer, where apart from the interaction with the surface, other forces become important. And then there is free atmosphere, right? Free atmosphere, that's where we fly the planes from Mexico to Australia, and even there we still can feel turbulence from time to time. That comes from the surface, where, of course, all the fluxes are facilitated by the waves. So the last slide for the introduction How do we do that now, right? On the left, you see the schematics, the atmospheric models on the top. We're talking about Earth interactions here. The ocean models are at the bottom, and they talk directly to each other. So they simulate phenomena like in the atmosphere, the tropical cyclones, weather, climate, which include the physical processes of turbulence, boundary layers, winds, and in order for the atmospheric model to talk to the ocean model, it has to simulate fluxes of momentum, of energy, of spray, which includes moisture exchange, aerosol exchange, heat fluxes, and so on. And the ocean model receives them, right? But in fact, if you think of those fluxes, the momentum flux, the energy flux, they're supported by the waves, right? We parameterize them somehow in terms of the drag coefficient, for example, which we will spend quite some time talking about next, right? Drag coefficient is just a parameterization, which has a lot of scatter, right? But what does it try to describe? It tries to describe the momentum flux. And if you put the wave model into there, right, and the wave model's right here in the middle, uncoupled just yet, right? Then you don't need to parameterize those fluxes, right? Because in the wave model, there is wind input. That's the flux which the waves receive. So where does it come from? Well, that's the flux which atmosphere is losing, right? And then you don't need to parameterize this flux. So you know exactly what it is if the physics of the two models talk to each other. This effect of the exchange of the momentum and energy between input, between the atmosphere and ocean has to be modeled with caution, right? Because the wind, apart from the waves, also creates currents, right? And if you couple the wave model into the ERC model, you get the flux which goes to the waves, but you don't get the flux which goes to the currents, right? We have to remember about that. But we'll discuss that a little bit later. But at least you don't need to parameterize the flux which goes to the waves if you have the models coupled, right? Now, on the right, you see some bullet points where the wave induced fluxes come into. When we think about these fluxes in non-dimensional term, you also need to understand your length scales. As far as the waves are concerned, and they influence in the air and in the water are concerned, we have two scales, two length scales. One is the wave height, right? At the scale of the wave height in the atmosphere, you know, there's no turbulence, right? It's directly wave-induced pulsations in the atmosphere. And in the ocean, there is wave breaking produces a lot of turbulence at this scale. And then there is wavelength. At the wavelength, right? That's the scale at which the atmosphere knows that the surface is present and that surface is covered by the waves, right? And that's the same on the ocean side, right? So there are two scales, and then on the atmospheric side, the waves form a separate boundary layer, which is very different to, you know, the wall layer, right? If we study turbulence or we teach turbulence, right, there is wall layer and there is floor and there is a no slip conditions and there is a logarithmic profile, right? We still have logarithmic profile over the ocean surface, but the dynamics there is different because of the wave produced pressure pulsations in the wave boundary layer. So we need to understand how it works. And of course, then waves produce and inject spray. As I already mentioned, that spray evaporates, produces aerosol. Aerosol goes all the way up to form clouds, right? And greenhouse effect is due to the clouds. So there is plenty of connections here for studies, for research, for applications in Earth interactions these days. On the surface, that's exactly where the waves are, or ice is there, right? I don't want to spend too much time here, but I want to just highlight that the dynamics, thermodynamics of what happens in the surface is different for light winds, for moderate winds, and extreme wind conditions. right? Light winds, let's say less than 7-8 meters per second, there is no wave breaking. There is no wave breaking. You can imagine that the dynamic is very different, right? Now, at extreme conditions, spray is produced, right? There is flow separation. There is a lot of things there, right? So again, the extreme conditions, the Earth interactions are continuous. And then there are conditions between light winds and extreme winds. Of course, we have to keep in mind this difference, right? Because the tradition is we get some parameterization. Usually that's in moderate conditions, and then we extrapolate that to extreme winds, and then we extrapolate them to the light winds, right? And of course, if you extrapolate something to extreme winds, the winds go stronger, you will get bigger waves, right? But it's essentially different environment for the Earth's interactions. So bigger waves, but you will never be predicting something accurately, right? And the same for the light winds. So we have to understand this difference in the dynamics in the physics of Earth's interactions. Below the surface, there are very important influences of the wave-coupled processes. I'm not talking about today, and there are a lot of dynamics, wave-coupled dynamics in the coastal areas. Right? Again, I mentioned them for completeness here, but I will not be concentrating on them today. Moving to the sea drag, so moving from the introduction to the actual topic of the atmospheric boundary layer, and I already spent half an hour on my introduction, so I have to speed up a little bit, but remember there are 2 more lectures, right? If you have patience, then you can learn all of that, what I was going to say, right? So the sea drag, I mentioned it a couple of times already, for a good reason, because when we talk about the Earth's interaction, it's the coefficient, the drag coefficient, it enters Earth's interactions in all models for the large scales. That's the weather, if it's marine weather over the ocean, that's the ocean circulation, that's the marginalized zone, that's climate, that's everything. The drag coefficient, if these models are Earth's interaction models are not coupled with the wave model, right, then drag coefficient, that's all what they know about waves or about the surface, right? Now, what is this magic coefficient? Right, this coefficient is was designed for good reason by obviously some very smart people about 40 years ago, right? And it served well, but the problem is that because it's just a number, right? It has a very big scatter, and what you see here in the top right corner is actual my measurements of the drag coefficient. These are accurate measurements, as I will try and show you in subsequent slides, right? But the scatter is, which we see here, is a 300-400%, right? So that's because you replace the whole dynamics of the boundary layer with a single coefficient. Now, what that was meant to mean to begin with, right? So to describe the Earth's interaction, we need this tau, right? You see tau, and that's the vertical flux of the horizontal momentum, or a wind stress, as they also call it. That basically means how much momentum the wind loses and passes to the surface, right? That's what it is, right? So the wind has momentum, it's moving air, and it gives it to the surface. So that's what we need to describe the Earth's interaction. Now, this flux is turbulent, right? So we basically need to measure turbulence, U prime, W prime. That's the product of the horizontal oscillations of the wind speed with the vertical oscillations of the wind speed, right? And that would be our turbulent flux. But we can't measure that. I mean, we can, right? But it's difficult and is usually unknown, right? The actual measurements of the turbulence usually unavailable. And the meteorological models, they usually don't produce that, right? Produce only the mean wind speed, right? So is I don't know who is credited with the invention of the drag coefficient, but at some point somebody, right? They said, well, this product U prime W prime, right? It has a dimension of the velocity squared, right? And so does the mean wind speed squared, right? So we just put some coefficient here, drag coefficient in front of that. And then if we know the mean wind speed, and we usually know that, then we get the momentum flux, right? And that was the idea, right? But of course, these are very different physical properties, the mean wind speed and the momentum flux. For the same mean wind speed, you can have different momentum flux. It depends on atmospheric stability or characteristics of the surface and so on, right? That's where scatter comes from. Scatter, when we measure the drag coefficient, doesn't come from the fact that we don't know how to measure that. It comes from the fact that it's a complex boundary layer, right? Over here in the definition, you also see U star, which is called friction velocity, right? That's just another name for the momentum flux. U star is actually not a velocity anywhere in the physical space. The meaning of U star is the square root of the momentum flux. That's what it means, right? So let's keep in mind that, right? So U star, when we have that, we're talking about momentum flux, right? U10 is the mean wind speed, and the drag coefficient is this coefficient which connects the mean wind speed and the momentum flux. And of course, if the mean wind speed goes bigger, on average, the momentum flux also goes bigger. But that's not a unique connection here, right? But we have to rely on this parameterization for the RC interaction models, unless we get this momentum flux directly, say, from the wave model. In the wave model, we get it. But we have to be careful about that, right? Because part of the momentum flux goes to generation of the currents, right? So I took this picture from the old paper by two Vladimirs, Kudryavtsev and Makin, and the vertical scale here is the total momentum flux, right? It's in percentage, so 100%, one is 100%, right? Now the horizontal scale is the wind speed, right? And the dashed dotted line here shows the momentum flux, which goes relative momentum flux, right? In percent, right? Which goes to the currents. And the two other lines say the momentum flux, which go to the waves, right? And Vladimir's, they subdivide that into two parts. One is with braking, another without braking. You just add them up, right? So that's the momentum flux, which goes to the waves. And you see that at light wind speeds, right? Let's say below 7 meters per second, the most of the flux goes to the currents, right? At strong wind speeds, most of the flux goes to the waves, right? And the percentage of what goes to the currents goes down very significantly, but it doesn't mean that it becomes zero. It's just percentage by comparison to what goes to the waves, right? But the currents for stronger winds are still going stronger, right? So what I'm trying to say with this slide is that we are talking about coupling, and not just in academic context, right? But in the practical context. If you model the ocean, right, and you get the fluxes from the wave model, that is fine, right? But there is also always part of the flux which ocean model doesn't support because it's supported by the currents, right? And in the practical modeling of the ocean circulation, if we use a wave coupling, we have to remember about that part. Otherwise, we'll be missing on production of the currents. But anyway, let's go back to the drag coefficient. And this is an old paper which Vladimir Makin and I wrote. And we said, well, there is drag coefficient, and it has such a big scatter because it's parameterized in terms of the wind speed. But apart from the wind speed, the drag coefficient depends on other properties in the ERC, near the ERC interface. That's the sea state, that's the wave steepness, that's the flow separation, that's the gustiness of the winds, and so on, and wave breaking, and so on and so on, right? And we counted 16 influences with Vladimir in that paper, which was 15 years ago, right? And now I probably could count even more, right? So what does that mean, right? If you want to get rid of the scatter, well, you have 16 separate parameterizations, right? Which predicts their influence on the drag coefficient, which becomes just impractical to begin with. Secondly, you don't know all those influences, like gustiness, for example, right? Or you can just couple with the wave model, and it tells you exactly what is the flux that the wave model receives, and that's the flux which is lost by the wind. Right, so we then investigated the drag coefficient through the measurements which we did at Lake George. Lake George are in Australia near Canberra. There's a picture of our observational site. There is an anemometer mast here. That's the schematics of the anemometer mast. All right, and it measures winds at 10-meter high, and then there has 6 wave probes all the way down to about half a meter above the ocean surface. So we actually measure the wind profile, right, with this anemometer mast. Somewhere in the middle of the anemometer mast, there is a sonic anemometer, which actually measures 3-dimensional turbulence. Remember, I told you that the momentum flux is the turbulent flux. So we also measure that, right? And therefore, we can get the estimate of the drag coefficient by 2 different, completely independent means, right? And that gives us confidence that we measure that correctly or incorrectly, how well it is measured. So how does it work, right? The drag coefficient, you already saw this formula, right, which is the definition of the drag coefficient, right? So basically, we need to measure U10 wind speed, right, which we do, right? And we need to measure U prime, W prime, the turbulent flux, which we do in Lake George, right? And then the ratio of those two gives you the drag coefficient directly, right? Now, this U star, right, which is the momentum flux squared, right, defines the slope of the logarithmic profile. You see this 4 different profiles measured at the mean wind speed, 5 meters, 10 meters, 15, and then 20 meters per second. In the logarithmic space, they look pretty straight, right? So the slope is obvious, right? And that is your U star divided by kappa, right? So we know U star, which is the momentum flux, again, directly, right? And if we know the mean wind speed, we can get the drag coefficient by completely different method, right? And compare them to, and if they agree, of course, then we have some confidence that we measure that well, right? So here is a comparison of the drag coefficient measured from the profile and the drag coefficient measured from the sonic anemometer, the turbulent flux. There is 1-to-1 line, and they see if the very high correlation on that line. So we measure this drag coefficient correctly, right? Just to convince you that the slides which I'm going to show next give us the realistic picture of the drag coefficient. Now, if we look at the comparison of these 2 measurements for very light winds before 4 meters per second, right? Then they don't agree pretty well. I don't want to spend too much time talking about that now, right? Just keep that in mind, right? Let's say this turbulent measurement or profile measurements of the drag coefficient for very light winds, they're not accurate, right? But if you are more than 4 meters per second, we're good, right? So with all that lead up, let's have a look at this magic drag coefficient. So the vertical scale here is the drag coefficient. Horizontal scale in the first panel is the mean wind speed. That's how drag coefficient is usually parameterized. The right panel is the parameter U over Cp, which is we call it inverse wave age, right? That's how much wind is faster than the speed of the waves, right? In the wave science, that's an important non-dimensional parameter, right? Because the waves are dispersive, longer waves move faster than the shorter waves, right? And as the waves develop, they become longer and longer, they move faster and faster. Finally, they move with the same speed as the wind, right? And if the waves move with the same speed as the wind, U over Cp equals 1. These waves move in the still air, right? There is no wind for them, right? So this is the parameter which defines the wind force. If U over Cp is big, means the wind is much faster than the waves, it can still actually actively push the energy into the waves. And for the drag coefficient, of course, when U over Cp is 1, right? So the wind moves with the same speed as the waves, this roughness is moving for them. The resistance has to be lower, right? So there are parameterizations for the drug coefficient in terms of the U over CP as well. But anyway, let's concentrate on U10 because this is how it's usually done. Drug coefficient over U10. This is our measurements. I just showed you the measurements very accurate, right? The scatter is 300%. For the wind speed, 7 meters per second, we can have a CD 1 times 10 to the minus 3 or 3 times 10 to the minus 3, right? 3 times difference, right? So it's it's not error measurements, then what is it? And as the bullet point here below shows, the most distant outliers are those with the gustiness, right? So because we have a time series of the winds, we can make our conclusion about the gustiness of the winds. We can exclude the cases with the wind gustiness, and that's where we are, right? If the gustiness is less than 0.09, right? And you can read the paper to see the details of the definition of the gustiness, but basically that's the ratio of the oscillations of the wind speed to the mean wind speed itself, right? It's that's a relative non-dimensional thing. So if we include the gusty winds and we include the winds with the trend, because the winds are never constant, right? It's always grow or decrease, right? And depending on how fast they do, that also affects your measurements of the drag coefficient. So if we include the gusty winds and include the situations with the big trend of the mean wind speed, we reduce this scatter very significantly, right? So again, if you work with the drag coefficient, you have to keep that in mind, right? The gustiness contributes a lot into the estimates of the drag coefficient. All right, so we identified gustiness as an important parameter, but what can we do about that? All right, the meteorological models don't give us too much guidance on the gustiness. So even if we wanted to parameterize the drag coefficient in terms of the gustiness, we don't have information about the gustiness. And then this slide is rich. You can look up the details of those panels in the paper. I want to concentrate on this subplot where the gustiness parameter detrended, right, from 0 to 25% here is shown, is plotted as a parameterization as a function of the mean wind speed. There is a lot of scatter, but there is a clear envelope, right? And there is a parameterization for that envelope, which shows what is the maximal possible gustiness for this particular wind speed. For lighter wind speed, the gustiness is bigger. For stronger wind speeds, it is smaller. It asymptotes somewhere to 5%, right? So if we don't know what gustiness was in this particular case, at the very least, we know what the maximal possible gustiness was there, and then we can include that into our parameterizations. Interesting cases, interesting comparison is the comparison between the development dependence of the drag coefficient on the mean wind speed and on this U over CP ratio. At the right panels, we show the dependence where for when the gusty cases are excluded. Right on the left, in the left panels, they're still included. At the top, these are dependencies on the mean wind speed. At the bottom is dependencies on the inverse wave H, U over CP. So what we see here is there are kind of envelopes, right, for all the data, right? There are obviously no data points below these envelopes, right? So at least in Lake George, these data drag coefficients below those conditions defined by the envelopes, they don't exist, right? So if we're talking about the drag coefficient, we expect the drag coefficient be above those envelopes, right? And there are parameterizations for those envelopes. And there is interesting observation that they crossed, right, in terms of U10 and U over CP at some points, and that's where you expect the minimum scatter for the drag coefficient, right? Because both dependence on U and U over CP are overlap. in this point. But what I wanted to specifically mention here is that, and that's relevant for the observations that you do here in CICESE, right? I know that we have a student, right, with Pedro and Paco, right, who is working on the drag coefficient over swells, right? That in Lake George, we don't have swells, right? Lake George is a lake. There's nothing for swell to come from, right? It comes from the open ocean, from a distant storm, right? It doesn't happen in the lake. And therefore, the drag coefficient, the fluxes which we see here, the correct connection with the wind speed is for the wind-generated waves only, right? And for wind-generated waves, we clearly have this envelope, right? And we know the dependence for the drag coefficient on the wind speed for the minimal values of the drag coefficient on the wind speed for the wind-generated waves here, right? But in the open ocean, you can have swells. Swells can produce negative flux, and then the drag coefficient can drop below those lines, right? So we actually see more scatter when there are measurements in the upper ocean, right? And these lines can be kind of a guidance, a benchmark, right, where your purely wind-generated seas are and where the wind-generated seas are mixed with the swells, which can produce the negative flux. Now, what I also want to mention with respect to this figure is that we excluded gustiness here, right? But there's still quite a bit of scatter, right? There's about 40% difference here, right? Which is not small if that's the momentum flux which you put in the climate models and model climate, right? However, gustiness, no matter how big its effect is not the only effect. You see this quadrats here, right? The drag coefficient measured with no gustiness and no wind trend, right? They're not sitting at the bottom of the envelope. They still sit in the model in the middle of the crowd. Of the data points, right? Which crowd still has a lot of scatter, which means that even after excluding gustiness and excluding trends, we have the scatter where some other influences are also important, significant. Now, continuing talking about that, I wanted to show the comparison with the other parameterizations which exist in this space. And the parameterizations of the drag coefficient, there are many, right? Because people have been measuring those for 40 years, and we're trying to produce some universal dependence, which then you can use in the Earth interaction models, right? I remember a publication by my colleague Guan Chanlong from China, right? You can look that paper. It's a nice collection of these parameterizations. There's about 40 of them, right? Now, they can be quite different, as I showed with the solid lines here in this picture, right? So there are Lake George measurements, and there are parameterizations. Some of them are obtained in deep water, others in finite depth, which are very different to each other. And if we talk about Lake George, then parameterizations obtained in the finite depths fit better the observations at Lake George, right? Why is that? Like this line, right? This solid line, it's the very accurate measurements, right? So everybody is saying, how can it be not right? Because this was a very detailed experiment, right? Done in North Sea. They measured that. That's the parameterization, right? So what connects maybe North Sea and Lake George, I was thinking, why is it Lake George agrees better with the parameterizations in North Sea than parameterizations in the deep ocean by Mark Donovan, for example, who also does did very good measurements, right? It's probably because the waves get steeper in the finer depths, right? And if they get steeper, that changes the flux, that changes the roughness, the friction from the point of view of the wind, right? And your momentum flux is increasing, your drag coefficient is increasing, right? So you can be introducing then dependence of the drag coefficient on the relative bottom, depth of the bottom, right? Or, as I said, we can just couple, the atmospheric model with the wave model, and then we can get this flux. So to finish this part of the lecture, I want to show you this slide where, based on the Lake George measurements, we plot the dependence of Z0, which is the surface roughness, right, for the logarithmic profile in the boundary layer versus U star over C, the inverse wave H parameter. Now, Z0, let me go back and show you the meaning of Z0. If you don't know that, then you will not appreciate this slide, right? So this logarithmic profile, if you measure the profile of the wind above the surface, right, is the vertical scale here is the wave height, is the distance from the surface. The horizontal scale here is the wind, right? In the constant flux layer near the ocean interface, you have logarithmic profiles for the wind, right? And the logarithmic profiles is defined, described by this formula, right? So U star is the slope of the profile. Z0 is the parameter surface roughness, which defines where this profile crosses zero, right? So at this height, the wind speed becomes zero, right? That's the meaning of Z0. Where it is on the surface, on the ocean surface, the meaning of this parameter is very obvious, right? So if the wind was blowing over this auditorium, right, then Z0 would be the order of the height of the chair, right? That's your roughness, right? But what is it in the ocean? In the ocean, Charnock produced this non-dimensional parameter for Z0, right, which connects Z0 to the momentum flux, to U star. And this is what is used for coupling of the ocean surface with the atmospheric boundary layer. In the ocean, as it is over the land. But over the land, Z0 has very clear meaning. Over the ocean, there is no clear meaning. For example, Z0 over the waves is of the order of 1 millimeter or something like that. So it's not wave height, it's nothing, right? It's just some parameter which defines this momentum flux. But look how scattered it is, right? So we were looking at the drag coefficient, which describes the momentum flux and the interaction between the surface and the wind, right? And that was the scatter of the water of the factor of 2, right? Now it's 2 orders of magnitude, the scatter, right? So Z0 is a very noisy parameter, right? And that's the parameter which is used in the coupled models. So I'm just alerting you to that, right? So again, right, we use parameterizations. Drag coefficient is not so good. We're not happy about that. But Z0, which is a standard parameter for this coupling, right, is just awful. It's 2 orders of magnitude, right? So you look at this flux, right? The Z0, changes more than 10 times. Now, what is interesting, and my co-author on this paper, Vladimir Makin, was particularly excited that Lake George fit the range of the parameters, these red dots here, between the open ocean observations and laboratory observations, right? And in the open ocean observations, there was some dependence, some trend for Z0 observed, and they used that in the coupling models. But there was argument in the community that laboratory data don't show that, right? So something is wrong, either with laboratory or with the ocean measurements. But actually, Lake George, which these red dots, which is in parameter spaces between laboratory and the field, fits nicely between them, right? So there is no surprises here. Just indicates again that the scatter is big and the trend is not regular, right? So it's probably not the best parameter to be used for the coupling. And my hour is up, right? And I'm right here. I don't know about questions, Paco, but here are my conclusion. The drag coefficient does depend on the wind, but also depends on very many other parameters if you want to improve its parameterizations. And if we do want to improve those parameterizations, then we have to parameterize them separately, or instead we can just do the wave coupling, right? And include the wave models in the models for the Earth interactions. Now, the most significant outliers, right? If you can't improve everything, then the very little, the least that you can do is to remove the cases of the gusty wind, right? So those they produce the most distant outliers. Once you remove them, your scatter is about 40%. If you have them, you scatter about more than 100%, 300%, right? And also Lake George dependencies, which I showed here, they can separate the cases of purely wind-generated waves, where there is no negative flux. There is this envelope, right, from the cases in the open ocean, when you also have swell, and swell can, apart from receiving the flux from the wind, can give the flux back to the wind. So that would be all for this hour. Thank you.
Okay, we have some time for questions, please.
Alex, thank you for the talk. Very interesting. And in the case of gustiness, will you expect a logarithmic profile during? I mean, do you expect the formation of a logarithmic profile when you have a lot of gustiness? I mean, it's right to approach the problem with a logarithmic profile when the wind is changing a lot in time, in space?
Well, Pedro, this is kind of philosophical question, right? Because if this drag coefficient definition, right, it assumes that everything is stationary. This assumption is there, right? So if the wind is not stationary, right, it's a gusty, or it's a increasing, decreasing, or it's turning, we shouldn't be using it, right? Because that's not the fluid definition, fluid dynamics definition for the drag coefficient anymore, right? I can tell you more, right? That this same definition of the drag coefficient is used for swells, right? But for swells, this is no logarithmic profile where, you know, the profile connected to the surface, the speed is maximum at the top and is lowest at the bottom. It's the other way around, right? Imagine the swells enter the area where there is no wind. They start generating wind, right? Because they bring the momentum flux. So the maximum wind speed will be at the bottom, right? And then will be decreasing, right, towards the top. And there are good researchers about that, right? The University of Uppsala group in Sweden, right? They measured this profile, right? But in reality, in the models which are used for Earth interactions, we use the drag coefficient. And even in the case of swell, it's assumed like there is wind speed, and you divide it by something, and you get U star, right? So what is how can I answer? We shouldn't be using that. But for now, we don't have other parameterizations, right? So we need to couple waves. But when we do couple waves, right, then that's I mean, you can't just take the existing models and just couple them. You have to check whether you get the fluxes correct.
Okay, yeah, because I was thinking about the differences when you have a strong gustiness. And also I have another question. In the stress, most of the stress depend on how rough is the sea surface, right? And you parameterize CD in terms of the inverse of wave age. Yeah. But you use CP, I mean, the frequency of the phase velocity of in the peak of the spectrum. But this is probably pretty far from, in terms of frequency, from the the rough waves, I mean, the small waves. What's the idea? Physically, what's the reason CD depends a lot of the inverse of the wave age?
Okay, Pedro, three components to my answer to your question, right? First of all, I'm not advocating this. I'm against this, right? It's not against this, right? I'm saying that these parameterizations have problems, have some principal faults, right? And how we improve them, right? We can have more sophisticated parameterization, or we can include waves into the ERC models. Then we don't need drag coefficient at all, right? Because drag coefficient gives you the flux, so you get it from the wave model directly. It's no need for the drag. That's what I'm saying. Now, the reason we using when we do wave H UOCP is historic, right? So historically, you know, the non-dimensional parameterizations were introduced by Mitsuyasu and then by John Schwab. They were very successful in describing many things, right? And therefore people use them. And the parameterization there is based on the spectral peak. What you're saying is that the waves at the spectral peak, if they developed, they don't interact directly with the wind, right? Like if the wind is 10 meters per second and the waves phase speed is 10 meters per second, well, these waves don't interact with the wind. Why do we use them for parameterization? Well, look, they still, the reason these 10 meter per second waves appeared, that's because there are these small waves which are getting energy from the wind, and then by nonlinear interactions, pass information to the peak waves, right? So they're still connected. They're not completely disconnected, right? So if you increase wind speed, there will be longer waves, right? So there is a connection. So it's not completely senseless. So that's three components. But number four, right? If Pedro, if you want to suggest the parameterization, not in terms of the wind speed, but in terms of the waves at the spectrum tail, which actually get directly energy from the wind, I think that would be a better parameterization, right? I think that will reduce the scatter of the parameterization for the drag coefficient as a function of U over CP, but in your case, there will be not CP, but it will be phase speed somewhere at the tail, right? So, yeah, that's probably the way to reduce the scatter of the parameterizations, right? But I like the way to just couple with the wave models. But you know, coupling with the wave models is expensive in terms of computations, right? So sometimes you just need the fast parameterization, right? And if you can improve that, that would be good. I know that you have good students and they can and good measurements, right? So they can do that.
Basically, sorry, the question is because it seems to work very well. I mean, if you compare with when you put the CD in function of just U10, there is a lot of spreading and a lot of lines there. But it seems that if you use the inverse of wave H, everything works better. I was asking about the why. What's the reason of that?
Look, there are not that many parameterizations in terms of the wave H, right? They have been offered, but the community didn't take up on them. Some people use them, but I would say 90% of people use parameterization in terms of U10 still, right? So must be a reason, you know, they're not that big improvement, right? Maybe in some cases even worse, right? I don't know, but this is a very large community for ERC interactions, right? And very few people use parameterizations of drag coefficient as a function of U over CP rather than U10.
More questions or comments?
Oh, I have a little question. In the paper that you show, you say something about the drag coefficient could modify the directionality of the waves. I read in some part of the paper.
Drag coefficient
could modify the wave directionality.
Could modify the wave direction?
Yeah, the wave direction, yeah.
Drag coefficient?
Yeah. I read in some part of the paper you show something like that. or I get confused and I misunderstand.
Can you tell me which?
El de 2008, 20, that side.
Yeah.
No, the after the paper.
2008.
2008.
This one?
Yeah, the number 13.
So, okay, so the waves, the direction of the waves can modify the drag coefficient. Yeah, look, absolutely, you can do that, right? So let's say there is wind following the waves, right? There's one situation. Then there is wind against the waves. It's completely different situation, right? And there is everything in between, right? There are publications on that, right? Where people looked at a drag coefficient as a function of the direction of the waves, right? I think the maximum is when the waves are perpendicular to the wind, right? This also, I mean, how can this happen, right? This wind and there are waves generated by the wind. How can they be at angle? The most typical situation for that is tropical cyclones. Tropical cyclones are small, right? The winds are very strong and the cyclone is moving fast, right? So the way the cyclone was here, the waves were generated here, and then the cyclone is moving and the waves following it, right? Then on the right-hand side of the cyclone, tropical cyclone, right, the waves follow the wind. On the left-hand side of the cyclone, the waves are against the wind, right? Because they're coming from behind and the wind is now against, right? So, and there are two quadrants, pardon me, where the waves are more or less perpendicular to the wind. So you have all sorts of measurements of the drag coefficient as a function of the direction, right? And it has very clear dependence on the direction of the waves with respect to the wind, right? But if we think in terms of the fluxes, right? Then there is what happens, right? There is wind, right? And there is surface, right? And in the surface, there was roughness due to the waves like this. And in this quadrant, the wind is still there, but the roughness is like this, right? So it's like if the wind blows, along the auditorium, and the chairs will provide roughness, or it blows along the chairs, right? And the roughness is different, right? Yeah.
Another question, Alejandro.
Well, this is very, very interesting topics covered here. I have one question. You mentioned all these possible physical or let's say components of the on the impact on CD. What about analyzing because the measurements in light of different wave conditions, directionality? Can it be done? I mean, because you have this scattered for long time series, and you obtain one dot, 1 point, right?
Mm-hmm.
What about selecting different conditions for analyzing the data? Is it possible?
Absolutely.
So you can analyze the effect of all these parameters differently, right?
Yeah. Look, thank you for this question. That gives me an opportunity to advertise the second part of my talk. I will give examples of that. Yeah.
Thank you.
More questions? Yvonne?
Hello, thank you so much. It was like very insightful to see all this. I think it's a lot of information to process. I'm very interested in ocean atmosphere interactions, but I'm mostly focused on large scale. So I have a couple of very basic questions. The first one is, at the beginning of your introduction, you mentioned that, and actually you make the point that it's important to, to use couple models. And I think you are meaning ocean atmosphere waves models, right? So including the three phases. So not only ocean waves, but also including the forcing from the atmosphere in a couple model, right? So when you, Yes, so I'm just asking, when you are talking about that it's important to do couple models, you mean couple models for the ocean, the atmosphere, and waves, right? Because right now this is, you have them split into 3 different kinds of models, right?
Get closer to the microphone, please.
Yeah, okay. Yeah, well, look, for the waves, it is important as well, right? Because obviously, in the coupled environments, the wind produces waves, but the waves change the wind, and then we keep modeling the waves, right? We need to know what these changes are, right? Also, the waves contribute to the currents, right? I didn't talk much about that, right? But when the waves break, they lose momentum, it goes to the surface, right? So it produces currents, which are not just surface currents, right? Because they depend on what the momentum of the waves was, right? But, you know, in the wave modeling community, we deal with that all right? So, of course, we can improve the wave forecast by coupling. But if we talk about some basic properties like wave height, right? They're already pretty good. Like we model for the full year with the bias, the RMS scatter maybe 5-7% globally, right? But where it is really important, right? That's in the large scale models, right? That's what you're doing, right? If you're doing atmospheric model, you know, traditionally all they know about the surface is drag coefficient, right? But drag coefficient can, for the same wind speed, right, can be, you know, 2 times different, right? Okay, and then this is something that goes into modeling of the atmospheric circulation, right? But the accuracy there is 100% scatter, right? But if you include the waves into the atmospheric models, right, there is no scatter. Because the integral of the wind input in the wave model, right? That's the flux which is lost by the atmosphere. So there is no drag coefficient anymore, right? So I think for large scale models, this coupling is much, I mean, can bring much more than it would bring to just wave model.
Right. And in that same line of thinking, are you aware, because I mean, as far as I know, all the CMIP6 models, or most of them, I'm sure does not have a wave model, right? So I wanted to ask you, do you know if the CMIP6 models, for instance, already include, or at least some of them, wave coupling with the ocean, or not really?
Not really. It's like you know, there are research models which do that, right? And tomorrow I will be talking about the fully coupled wave atmosphere, but in that case, that's WRF for tropical cyclones, right? In the ocean. And please come, you will see the difference, right? But the major atmospheric models, right? They're not coupled, right? And that's what the conference series, which I was advertising in the very beginning, is about, right? We're trying to bring these people from different communities so they talk to each other, right? It's like wave models, we can present these coupled approaches to each other, okay? But the atmospheric models don't hear that, right? So we need to come to some joint venue, right? So please come to our conference, right? But what I'm also need to say here, right? And I kind of mentioned that, right? That the coupling in the atmospheric models with the surface is usually done through Z0, right?
Yes.
And Z0 is such a scattered parameter to begin with, right? Even worse, I mean, not worse, I mean, drag coefficient has a big scatter, but everything in the environmental modeling has a big scatter, right? But Z0 has much bigger scatter. That's one thing. Another thing is that when we talk about atmospheric coupling with the ocean, part of the atmospheric flux, of the momentum flux from the atmosphere goes to the waves. Another part goes to the currents, right? If you look at the atmospheric boundary layer, it's logarithmic, which means it has constant flux. So whatever height you measure, it's constant, right? So if you measure the fluxes for the waves separately and for the currents separately, you just add them up and it's the same constant flux which is at the top of the boundary layer, right?
Okay.
But if you have separate Z nodes for the waves and for the currents,
Then,
it doesn't work. They don't add up, right? They don't even have clear physical meaning, but that's how the atmospheric coupling is done now, right? So somebody has to rewrite the way the atmospheric models talk to the ocean surface in terms of fluxes. And then coupling with the waves will be really useful.
mhm. Okay, yes, thank you so much.
Then I think we should consider another way of approach, like thinking that the stress is a vector, and then
yeah.
forgetting about the CD
Yeah.
and talking about more as a vector, and then you will have to consider or detect the direction of that wind stress compared to wave direction or current direction or wind direction, which is some part of the work of Carlos that you know. That then instead of only CD, we are talking about the wind stress as a vector, which might give us a better position.
Yeah, Paco, this is absolutely right. And if you do coupling, direct coupling of the atmosphere and the waves, right? Then this issue with the stress vector is kind of resolved automatically, right? Because drag coefficient is a scalar. It doesn't know, right, that the waves go at some angle and it has to change, right? It just has a wind speed, right? That's what Miyake asked about, right? But the differences can be there. I mean, they are there. We know about that. Yeah.
Right. Any more questions or comments? No. Otherwise, we thank Alex again. And you are all invited to some cheese and wine and beverages and things that you're welcome.